Hello and welcome to this GCSE Physics exam preparation video. This is Electricity 1, Current Electricity. There are two types of charge, positive and negative. These charges attract or repel according to the following rules. Like, the same, charges repel. Unlike, opposite, charges attract. To make an object charged, you have to rub it with another object. Both objects have to be insulators, or any accumulated charge will be earthed. The rod and cloth start off uncharged. They have equal numbers of positive protons and negative electrons. Once the cloth has been rubbed against the rod, electrons transfer from the cloth onto the rod. The extra negatively charged electrons give the rod an overall negative charge. The cloth has lost electrons and so has been left with an overall positive charge. When an object becomes charged, it's always the electrons that move. This is because they are held to the atom with less force than the protons are, so less work is needed to get them to move. A Van de Graaff generator charges by rubbing a band against a metal brush inside the dome. This removes the electrons, negative charge, from the dome, leaving behind a positive charge. The earth rod is connected to the earth circuit and so has no charge. If the potential difference between the earth rod and the dome is big enough, electrons will jump or arc from the earth rod to the dome. You will see a spark when this happens. This will balance out the positive charge on the dome and the dome will have been discharged. An electric field is an area around a charged object where the force of that charge can be felt by another charged object. Here we have two diagrams showing the electric field around a positive charge and a negative charge. The lines represent the electric field lines, and on them are arrows that will show whether it is a positive field or a negative field, regardless of whether you actually have the charge shown in the centre as I have here. The arrows show the direction that a second positive charge would move if it was placed in that field. So if you place a second positive charge in a positive field, then it will be repelled and the arrows move outwards. If you place a second positive charge in a negative field, then the positive charge will be attracted and so the arrows go inwards. These diagrams show how the electric field is represented. Where the field lines are closer together, nearer the charge, the field is stronger. Further away, the field is weaker, and this is shown by the field lines being further apart. Circuit symbols are agreed symbols that are used to show how components are arranged in circuits. These are the list of circuit symbols that you need to know. You need to be able to recognise and to draw them. This diagram is directly from the AQA specification. There are several terms that you need to understand to get to grips with electricity. Charge. Charge is measured in coulombs. The symbol for charge is Q and the units are capital C. Charge can either be positive or negative. The smallest amount of charge you can have is the charge on one electron, which is minus 1.6 times 10 to the minus 19 coulombs. Or it could be the charge on one proton, which is positive 1.6 times 10 to the minus 19 coulombs. Notice that they are the same amount, but the electron has a negative charge and the proton is positive. In electrical circuits, we are usually concerned with electrons flowing around the circuit. Current. This is the flow of charge in a circuit and it's measured in amps. The symbol for current is capital I and the units are capital A. Charge and current are linked by the following equation, and it's one that you need to learn for your exam. Q equals I times T, which is charge equals current times the time. Time needs to be in seconds, so you may have to convert from minutes. So 1 minute is equivalent to 60 seconds. So you would need to multiply the number of minutes by 60, and that would give you the number of seconds. Potential difference. This is the difference in ability of 1 coulomb of charge to do work between 2 points. It has a symbol of capital V and the units of volts. The symbol is also capital V. Voltage is related to charge with the following equation. E equals Q times V. This is an equation that you need to learn. And its energy equals charge times the potential difference. Resistance. This works to slow the flow of charge. The greater the resistance, the smaller the current. Resistance has the symbol capital R and the unit is the ohm. Resistance is related to potential difference and current with the following equation. V equals I times R. And again, you need to learn this equation. This is potential difference equals the current times the resistance. From this equation, you can see that the larger the potential difference, the larger the current, and that the smaller the resistance, the larger the current. The equation that can be used to calculate resistance is V equals IR. Potential difference equals the current times the resistance. So to find the resistance of a component, the potential difference and the current have to be measured. The resistance can then be calculated by using the equation above. This is the circuit for gathering this data. The ammeter is in series. It measures the current going through the component. The voltmeter is in parallel with the component as it measures the difference in potential to do work, so needs 2 points to compare. You also need a variable resistor in the circuit to vary these readings so you can get multiple readings in an investigation. Take readings of current and potential difference and substitute them into the equation to calculate the resistance of the component. Using this circuit, data can be gathered and plotted. To get data in the negative direction, reverse the power supply. Different components have different characteristic graphs. You need to be able to match the shape of the graph to the components and be able to explain the shape. This circuit is set up for a fixed resistor. If you swap this for a filament lamp or a diode, you can get data for those components. This is an IV graph for a fixed resistor. Its characteristic shape is a straight line that goes through the origin. This shows that the current and the potential difference are directly proportional. This type of graph shows that the component is an ohmic conductor. That's one that obeys Ohm's law. Ohm's law is that the current and the potential difference are directly proportional as long as the temperature remains constant. This circuit is set up for a filament lamp. This is a graph plotted from data gathered from the circuit above. This is the characteristic shape for a filament lamp. It's not directly proportional as it is curved. This shows that it does not obey Ohm's law and so is non-ohmic. The graph curved because the resistance of the filament lamp changes. This happens because the lamp gets hotter and therefore the lattice ions in the wire vibrate with greater amplitude. A greater frequency of collisions with the electrons is now possible and this reduces the current. This circuit is set up for a diode. A diode will only allow current to flow in one direction. This is a graph plotted from data gathered from the circuit above. It is the characteristic shape for a diode. It is not directly proportional as it is not a straight line that goes through the origin. This shows that it does not obey Ohm's law and so is non-ohmic. The graph has this shape because the diode has a really high resistance in the negative direction. No matter how high the potential difference is, no current will flow in that direction. If the current is in the positive direction with respect to the diode, then current will flow once a threshold voltage has been passed. After this, the current will increase with the potential difference. This is the symbol for an LDR, a light-dependent resistor. The higher the light intensity, the lower the resistance. Uses are to control streetlights. As it gets darker, the resistance of the LDR increases, and this lets a second circuit switch on the lights. This graph shows you how the resistance changes with the light intensity. This is the symbol for a thermistor. This resistor changes its resistance depending on the temperature. The higher the temperature, the lower the resistance. A use is to control thermostats in central heating systems. When the temperature in the room is high, the resistance of the thermistor is low, and this turns off the central heating. When the temperature in the room is low, the resistance of the thermistor is high, and this turns on the central heating. The graph shows you how the resistance changes with the temperature of a thermistor. This is a diagram of a series circuit. It only has one loop. Because of this one loop, the current can only flow along this one pathway. This means that the current is the same everywhere in the circuit. Potential difference in a series circuit is split between the components in the circuit, but the total potential difference always adds up to the potential difference across the power supply. This is a circuit diagram for a parallel circuit. It has more than one loop. Because of this, the current can flow in more than one pathway. So at the junction, the current splits. Some of the electrons go along one branch and some go along another. When the current joins at the other junction, it adds together and results in the same total current as before the split. Potential difference is the same on each branch, and this value is the same as the potential difference across the power supply. To find the total resistance in a series circuit, add up the values of each resistor. So here we have series circuits, and we have resistors of value 3 and 5 ohms, and that gives a total of 8. Another circuit with resistors of value 7 and 10 ohms, which gives us a total resistance of 17 ohms in that circuit. This next series circuit has resistors of values 3 and 2 ohms, which gives us a total resistance of 5 ohms. And this final circuit, it has 3 resistors in it of values 1 ohm, 10 ohms and 11 ohms, and that gives us a total resistance of 22 ohms. In a parallel circuit, total resistance can only be described as being lower than the resistance of the lower value branch. As more branches are added, the resistance will get lower because the current has more pathways to flow along and so will have less resistance to overcome. So in this first example, we have parallel resistors of value 3 ohms and 5 ohms. And all you can say about the resistance in this circuit is that it will be less than 3 ohms. In this next example, we have a 7 ohm resistor in parallel with a 10 ohm resistor. So the total resistance for this circuit will be less than 7 ohms. A 3 ohm resistor in parallel with a 2 ohm resistor. So our total resistance is less than 2 ohms. And in this final example, we have a 1 ohm resistor in series with an 11 ohm resistor, and they are both in parallel with a 10 ohm resistor. Because of our series ones, you add them together, that gives us 12 ohms on that branch, as opposed to 10 ohms on the second branch. So we can say that our total resistance for this circuit is less than 10 ohms. And that's the end of this video. Thank you so much for listening.